So welcome to the part 8 of this series of presentations for abstract algebra course that I am teaching online. And the textbook that we are using is Abstract Algebra, Theory and Applications by Thomas Judson, a free textbook available online. And a reason I must mention the textbook is this, that I'm not going to cover each and every part in the lectures, and it is supported with the book and on the course page that is meant for the class that I'm teaching. So anyways, welcome if you chose to join this. All right, so let's go further. So in this part we are going to talk about cyclic groups. So consider a group. So consider a group with an element A in the group. What we do is we define the integral powers of A as this. We are taking A to the power 0 as the identity in the group, and A to the 1 of course is A, and A to the, A to the 2 is A composed with A, all right? And we can go recursively like this, that A to the power k plus 1 equals A to the power k composed with A. Okay, so and where k is a positive integer. So we got k is an integer and it is positive. Okay, an integer. Now, in case we have a negative integer, okay, say we have m equals n, negative n, where n is a positive integer, okay, all right. So n is a positive integer. So what we do is this, that we shall define, one moment, okay. So we shall define a to the power m as a to the, or rather a inverse to the power n, because a inverse is an element of G and we can do that. So it's pretty simple. I mean, if you look at it, I think I made a very simple thing too complicated. That is, if you have a to the power 4, what you got is a composed with a, how many times? 4 times, right? Okay. And say you got a to the power, say, negative 4, you have the same thing, and the only thing is, the only difference is that here what we have done is that we have taken a inverse composed with itself, okay, how many? 4 times, okay. All right, I should have again written it first, but anyways, so here you go. So this is what is meant by these powers, the integral powers. Now, if it so happens that G has an element A such that the entire group G is described by the powers on A. For example, I have to see what notation does the book use. I'll check it later. Okay, so symbolically, what we denote by this kind of bracket A is this, that is, we have a to the power n such that n is an integer. Okay, and so if this happens, then what do we say is that G is a cyclic group. Okay, all right, so G is a cyclic group if all its elements equal, sorry, some integer power, or you may say integral power, but integer power is better, of a single element in G. So an example is if you consider, say, Z plus. So we are considering this Z plus, or the group of integers with respect to addition. So what we have here is, if we look at the powers on n, and for addition, 1 to the power n is 1 plus 1, just add 1 to itself n times, and that will be n, where n is, of course, an integer. So you can show that the entire group of integers with respect to addition can be generated by powers on the single element 1, or as a matter of fact, you can even take it to be -1. I'll put that in one of the exercises. All right. Now, on the other hand, the group of rationals with respect to addition is not cyclic, because say, for example, we assume that, okay, if we assume that Q is generated by a single element, and of course that element will have to be non-zero. I'm not writing everything. All right, so that element has to be non-zero. So say we have A over B, where of course A and B are integers. Let me enlarge it. A and B are integers, right? A, B belong to Z, okay? And B is not equal to 0, okay? So if this is the case, or let's just think that as understood, because that's making our symbols complicated. Yeah, here, this is better. Okay, so this is the situation, and our A over B is not equal to 0, right? Okay, that is, it's not that B is not equal to 0 and A is equal to 0, because all the powers of 0 will be 0, so that cannot generate this this group. So if we do this, that considers, say, consider an element, say, for instance, A over, say, 2B. All right, then what must happen? We should have some integer n such that A over B to the power n should equal A over 2B, right? Okay, so for some integer n belonging to Z, okay? Now, if you look at this, this comes from a group with respect to addition. So A over B to the power n will have to be how much? N A over B, right? Because it's A plus A over B added with itself n times, okay? And n, of course, will have to be non-zero, because otherwise A over B will become 0, in contradiction to our assumption. So if we make cancellations, what do we get is this: n equals what? 1 over 2. Now 1 over 2, that's not in Z, so we get a contradiction, right? Okay, so therefore, okay, we cannot have any therefore we cannot have Q equals, A over B, where A over B is, described as stated above. All right, I'm becoming a little informal in writing things step by step. Okay, so here is an example of a group that is not cyclic, and then of course the group of real numbers with respect to addition will not be cyclic, and we can go on in that manner. Now you can see that the group of integers modulo n with respect to addition modulo n for positive integers n is cyclic, all right, because you can just verify that Zn is going to be generated by, just as in case of Z, this is generated by the element 1 or the equivalence class of 1 bar. And as I said, we will very simply, we will very soon stop putting these bars or everything over here. Okay. Now, and for, let's just take a particular example. We are in no hurry because it's not only one that can generate it. For instance, let's take, say, n equals 10. Okay, so here you can see Z10 is, let me just write it and bring it back to you. So you can notice this here, and again, it will be just a matter of just sitting down and verifying that Z10 is generated by 1. And at the same time, you may notice that there are other generators, like, it's, if you take all the powers of 3, they also describe Z10. Just do that at your own leisure. All right, with 7 also you have the same thing. And you just sit down and see how 9 works, because with 9 to the power 1 is 9. Then 9 plus 9 is 18, so modulo 10 will be 8. Then 9 plus 9 plus 9 is 27, modulo 10 would be 7. So it just goes in reverse order here. So so Z10 is cyclic with respect to addition, and there are 4 generators of this group with respect to addition. And actually, you may notice that if you have a generator, if any of these elements, generates or describes the entire group, then that element and 10, they have 1 as the greatest common divisor. All right. So in other words, what we have is that, say we take this in general, and say we are going to say that, say again, I'm continuing with that, say A bar equals Zn, all right, where we are assuming that 0 is less than or equal to A, and that is less than or equal to n minus 1. Okay, so if, or let's write a statement here. So this happens if and only if, that is, an element of this set would be, would generate the entire group, if and only if what we can show is that the greatest common divisor of A and N equals 1. Okay. Now let us go back to this integers modulo n, and again we are with respect to addition modulo n. All right. Now the book did that earlier, we didn't define it, that if we take un to be those elements from here, all right, such that x and n are relatively prime, I meant from here, all right, such that x and n are relatively prime, then we call that the set un. You may call it the set of units in Zn. Okay, so for example, if you look at this, if you look at U2, okay, so U2 will have only one element, right? Namely what? Simply 1, right? Okay, so U2 has only one element. If you go to U3, all right, then in U3, I think you will have two elements, right? Okay, so 1 and 2. Then U4, let me just list some of them and so that we can talk about it. So I'll be right back, okay? So here I wrote them out for you, and let me reduce this a little bit. So I went all the way up to 8, okay? And you call this UN, as I said, the set of units in Zn. So this is like 1 is the only elements that fits in this criteria for Z2, and all the others are listed. For U7, of course, all the numbers 1 through 6, the greatest common divisor with 7 is only 1. Okay, so there are these many. For composite numbers, they will be smaller. Okay, and you can see that UN is a group, okay, is a group with respect to the multiplication modulo n. Okay, I think we had seen U6, this subset to be a subgroup before, or that of U4. I think we had seen U4 before, but anyway, even I forgot what we saw. All right, so like this is a group with respect to multiplication modulo 2, and this is group with respect to multiplication modulo 3, etc., etc. Now, in addition, what you will note so is that all these subgroups are cyclic. So for example, this one is cyclic, generated by 1. Okay, now in this one, what happens? Of course, it cannot be generated by 1. So in this case, 2 is a generator. All right, we have 2. Then when we go multiplication modulo 3, 2 square would be 4, and that's going to be how much? 1, right? And likewise, this one, if I take 3, 3 is so first 3 is 3, 3 square is 9, 9 modulo 4 is how much? 1, right? And here again 3 should work. All right, so here just describe the powers of 3. All right, and you will see 3 square is 4 here, and 3 cube is going to be 2. All right, and 3 to the 4 is 81, that is 1. So everything is described, and here of course we can see easily that this is the cyclic group with 5 as a generator. All right, because 5, then 5 is square is 25, we get 1. And then 5, oh, just a moment. We have a typo here, right? Because this just can't be here, right? Okay, so 5, and 5 square is 1. Let me kick this out. I was just mindlessly typing. I'm sorry. So, and in here, when you go to this, if 7, all right, just check it for yourself. Say, for instance, look at who the powers of, say, 3 are. We have 3. 3 square is how much? Modulo 7. 3 square is 2. And 3 cube modulo 7 will be 6, right? And 3 to the 4 modulo 7 would be that. So that 81 would be 77 plus 4, so that will become a 4, right? And if I look at 3 to the 5, then what that will be 243. So 210 plus 33. So what is that going to become? Okay, so that's 28 plus 5. So we got 5 in here. So just a moment, another typo, but that's okay. We are uh, so now I'll just finish it because it's just becoming very tedious. Now we are going to go on 3 to the power 6. So that's this times 3. So 240 times 3 is 720. Then 9. So this one would be 700. Let me not make a typing error this time. So the answer would be how much? 1. So this is generated by 3. Okay, and the point of just boring you so much was this, that in here you can see this, that if we go modulo 8, all right, what happens is this, 3 square is going to be what? 3 square is going to be 1, all right, because 9 modulo 8 is 1. And same thing happens with 5 square, because 25 modulo 8 is what? That is also a 1. Okay, and then the same with, see, 7 times 7 would be 49, and 49 modulo 8 is 1 again. So each of them has order 2, all right? And so therefore, and of course, this cannot generate the whole thing because this is not going to produce anything other than itself. So for this one, we are not getting any generator. So U8 will not be cyclic, even though U2 through U7 were all cyclic. And there is a criteria we can take up later in which we can find out which of these will be cyclic and which of these will not be cyclic. Now let's just get two more terminologies which book defines, and I hope that you are reading the book, okay? But I didn't formally define, so let me just go ahead and define those and then go further, okay? So one terminology is this, that if G is a finite group, then the number of elements in the group G is called the order of the group G. On the other hand, say I have a group G and an element A in the group G, and the group may be finite or infinite, okay? So for A belonging to a group G, okay, I didn't write group, but let's have it understood, okay? The order of A is, okay, A is the least positive integer n, the least positive integer n, such that A to the power n is identity, okay, or the identity element that will exist in G. And if no such positive integer exists, if no such positive integer is available, okay, we call, or rather we say that the order of A is infinite, okay. So let's just go by the book symbol. The book denotes this, modulus of A as the order of A, okay. So the different books have a different notation, all right. So for example, if say we took this set R star, That means the set of non-zero numbers, real numbers according to our notation. Okay, so if we took this set, all right, then the order of -1 is how much? 2. Now here there is anomaly in symbols because I'm writing order of -1 is 2 because -1 times -1 is 2 and 2 is the smallest such number, right? Okay, and on the other hand, uh, if you want to see the order of say an element 5, that's going to be what? Infinity, all right? Or say we are going to take more such examples, okay? So, as another example, let's take this group of quaternions, okay? And you know that this is a group with quaternion multiplications. In this one, what you can see is that the order of 1, of course, is 1, right? And the order of -1 here again, like the previous one, is 2, but the order of I, okay, all right, would be what? I mean, if you look at I, then you have I square is -1, okay, and then I cubed is -I, right, okay, and then you have I to the 4 equals 1, right? Okay, so every other element other than 1 and -1, you can see that their order is 4. And actually so order of I as well as that of -I, okay, so all these elements have order 4 each. And also you can see in this case that every proper subgroup of this Hamiltonian group is a cyclic subgroup, right? Okay, because just examine all the subgroups that you get in here, and you will see that each one of them is generated by a single element other than the group H itself. All right, so here all the proper subgroups, right, of H are cyclic, right? And let's look at some more properties of cyclic groups. First of all, you can see this here, that the book does a good job of proving it, that a cyclic group is abelian. And of course, the proof is based on this criteria. Again, this is not a formal proof that if I have a cyclic group, then all the elements are of the type of integer powers on A, and in this case, AR times AS is A to the R plus S, and addition of integers is commutative, so we can interchange these. So a cyclic group is abelian, that becomes a theorem as shown in the book, okay? And you can see that the converse is not correct, okay? Converse is not true. And as an example, you can see an example that we just had a little while ago, because as you saw, this group of units in Z8, that is 1357 with respect to multiplication modulo 8, okay, that is not cyclic, remember? See, order of every element other than 1 is how much? That's 2, right? Okay, and it doesn't have any element of order 4. So, and this is an abelian group. So this is abelian, but is not cyclic. Okay, so but is not cyclic. All right. Now let me just summarize some important properties of cyclic groups, which we can list as a fundamental theorem of cyclic groups. The book proves most of it in different parts, and I didn't see it describing something like fundamental theorem of cyclic groups, but that is stated just in a very methodical manner, that if, or in other words, all subgroups of a cyclic group are cyclic. So if I have a cyclic group and if I take a subgroup, then all the subgroups are cyclic, and we are not going to prove it here. And the idea would just come from here. That is, say this is your group G, okay? Then if you take a subgroup, then that will have powers of that will have powers of A, okay? And then you just take the smallest positive power. I'll let you read the book, okay? Because the book does it very nicely. And then the second part is this, that the order of a subgroup of a finite cyclic group is a divisor of the order of group. So what it means is this, of the group, because I have a finite group. So say I have a group of order, a finite order, say n, all right, and H is a subgroup of that group, and the order of H is say R, then n will be, Rs for some integer s, okay? So that is R will be a divisor of n, okay? And all these nrs, they are all integers. I'm being lazy not writing them, okay? But in a formal situation, we have to write them all. And I'm going to post an outline of the proof of this theorem in detail in the in our course page, okay? And part C is this, that if G is a finite cyclic group, okay, is a finite cyclic group, okay, of order n. What does it mean? Actually, it's easier to say that the number of elements in G is how much? N, okay? And D is a divisor of n, okay? Let's just say positive divisor of n, okay? Then, so for example, say we have, if D is a positive divisor of n, then what we should have is n should be equal to D times k for some integer k, all right, for some k. So in this case, what we shall have is, and also, n being positive and D is positive, so k will also be positive then, okay? So what will happen? Then there is one and only one subgroup of order D, where D was a positive divisor, okay, of G, okay, sorry, of G, namely, that will be just the cyclic group generated by what? A to the power K. So for example, say I have, for instance, if I took, say, Z with, integers modulo 10, all right. Now I know that, say, this element, and I'm looking at the addition modulo 10 as the binary operation, okay, then in this case you can see that the element 5, actually rather the number 5 is a divisor of the order of this group, right? Okay, is just a second, is a divisor of 10. 10 is the order of this group, all right, and 10 equals how much? 5 times 2, okay, so 10 equals 5 times 2. So according to the this criteria, if you look at this subgroup, that is the subgroup that's generated by the powers on 2, right? And with respect to addition, what 1 square will be? That will simply be uh, just 2 modulo 10. Oh, sorry. Okay, I hope this copying pasting doesn't confuse you. Okay, and if you look at this subgroup, then the subgroup will be what? It will be a subgroup of order 5. That is, we got 2, then 2 to the power 2 is 4. Okay, 2 to the power 3 is 6. 2 to the power 4 is 8, right? And 2 to the power 5 is simply 0, right? So here we have a subgroup of order 5 and 10. But the main thing here is this, as an implication of this statement, that this particular subgroup is the only subgroup of order 5 in Z10. Okay, so for instance, remember this, we did this, that this U8 with multiplication modulo 8 is not cyclic, right? And in this case, you can see that 2 is a divisor of 8, right? But there are like 3 different subgroups of order. How much 2 here? This is the subgroup of order 2. This is a subgroup of order 2, and so is this one, okay? And you can, so of course we can just have by show and tell that this is not cyclic, because 5 also has order 2. But say we had this, for example, say we were looking at U16, okay, and I'll just tell you a reason why I just went to 16 right away. So U16 would be, let me just write it and bring it back to you. So these are the elements of U16, and of course we have multiplication modulo 16. Now here, if you look at 15 square, that's the same class as that of what? 225, right? Okay, 225, and if you divide 225 by 16, you shall see that 1 is the remainder. Okay, so we have like you can see, we have one subgroup of order 2, and who is that? That's this subgroup generated by 15. Okay, and say let's look at, say, for instance, 3 square. Okay, so 3 square is going to be how much? That is going to be 9. That is not a 1. So say we are just searching if there is another element or not. And I am kind of cheating a little bit because I know that we will be able to find an element. Okay, but and this is 25. So if we do this, take modulo 16, then that would work. It's 25 modulo 16 will also be how much? 9, right? So this doesn't have order 2, but the moment we hit, sorry, this guy here, 7, and now this would be the class of what? 49, and 49 if you divide it by 16, okay, what is the remainder? Remainder is 1, okay, so I have another element of order 2. So what happens here is that I have again more than one subgroup of order 2 where 2 is a divisor of what? 2 is a divisor of 16. So in this case, this just contradicts the fundamental theorem of cyclic groups, right? So both of them have order 2 and they are distinct subgroups, right? And let me just tell you like this, and I'm pretending that I'm doing it for the very first time. And again, we don't have the luxury of sitting together here, unfortunately. Okay, so now I'm going to go to 32, and you can see I'm growing in powers of 2. So let me again complete it and bring it back. No, I promise I would not take you to multiplication modulo 64 or then modulo 128. Okay, so in here, notice this, that, this is the unitary group, okay, modulo 32. And if I look at this, 31 square, that is going to be the equivalence class of, or this is going to be the same as the class of what? 31 square is 961. And of course, this is 32, so you can easily see 32 times 3 is 96, right? So it's 96 plus 1, and that's going to be simply how much? 1. All right. Now, we are not going to waste our time on like looking at the orders of these. We may try. We are going straight to 15, okay, somewhere in the middle. And here, if I look at this, 15 square is what? The class of 220, the equivalence class of 225, okay, and then this simply becomes what this will become. We are going modulo 32. So 2 times 7 is 14, right? So here we get 7 times 32 plus 1, and this will also become a 1, right? So in this case, what happened was we found two distinct subgroups, okay, 31 and 15, which are of order 2, but they are distinct, right? And again, that if this U32 is cyclic, then the fundamental theorem is contradicted. So let's just realize a statement based on this discussion, and again, using our fundamental theorem. Remember this, that U4, we found that U4, which was how much? Sorry about that. Okay, let me just take this from here. Okay, so say I took u4, okay, multiplication modulo 4. And who was it? Okay, that was simply 1 and 3, right? Now this was cyclic because this was generated by 3, okay? So in here we have a power of 2, but what happened was that the group is cyclic, right? And I had it right. I'm just feeling bad that I'm doing such long calculations. So this is cyclic, but we just inductively saw that if I took, say, the unitary group of, say, 2 to the power k, okay, and where what we have is our operation is multiplication modulo 2 to the power k, okay, 2 to the, let's see how nicely this writes. It's not too bad, okay. So if I look at this for k greater than 2, that means, and of course positive integer, okay, integer k greater than 2, then we may try to see that none of these will be cyclic, like u8, u16, u32 we already saw. And say we are looking at, so we are looking at u2 to the k, and I said I would not take you modulo 64 or modulo 128, but I'm still legally safe if I take k to be greater than 7. All right, I'm not going to do that. So here, look at this here. That is, if you look at 2 to the, and here, notice this, our k is at least 3. So 2 to the k minus 1, right here, this number. And say we go further below here, say for instance, we had taken 15, 2 to the k minus 1 minus 1. Now k is greater than 2, right? So both of these are odd numbers here, right? Okay, so since both of these are odd, they will be relatively prime to this. So they are. So both these will be, or if you want, you may say that, you may put them in, I don't know, maybe from next one we will stop dropping these, okay? That is, we will just understand that that bar is there, okay? So both these guys are in U2K, right? Because both of them are odd, so they will be relatively prime with this even number 2 to the k. Now if you look at this, if you look at 2 to the k minus 1 to the power 2, what do you get? You simply get 2 to the 2k, right? Okay, then minus 2 times 2 to the 2k, right? Okay, and then you get plus 1. And so what this is actually simply, if you look at the modulus, this is 1 because this is a multiple of 2, okay? And then if you look at this one, 2 to the k minus 1 square, okay, then that also becomes 1, as you can easily see, because this would be 2 to the 2k minus 2. It still will be at least 2 because k is greater than 2, minus 2 times 2 to the k minus 1. So that will be simply 2 to the k, okay? And then we have a plus 1. So this portion is a multiple of 2, okay? 2 to the k I meant, okay? All right. So what do we get? Because this is 2 to the k, all right, okay, and this one would be 2 to the k plus 1, all right, and here this is 2 to the 2k, or we may say this here, okay, 2 to the k minus 1, okay, or in fact, let's just write it separately, and I would not be apologetic for doing calculations. Okay, I'm just going to go to 2k minus 2 minus 2 to the k, all right, and then if I factor a 2 to the k out, what will I have is that I have 2 to the power k minus 2, and then I'll have minus 1, right? So since k is greater than 2, the minimum this will be is 1, right? So what happens is, you can see this is still a multiple of 2 to the k, all right? So the square of this modulo multiplication 2 to the k will be 1. So what we have just found is this, that both these, the subgroup generated by this and a distinct element this here, okay, they both have order 2, which is a divisor of 2 to the k greater than 2, okay, but they are distinct. So what we see is that u to the 2k, sorry, u2k is not cyclic for any k greater than 2, all right, okay, or let me just make it here, okay. So I shall just write some exercises for you, or let's just do this here, just one more example. I just stretched this example for too long, but it will take just few minutes, okay. Let's just take one more example. First, let me get this thing out of here. Okay, so now let's just take up the non-zero complex numbers with complex multiplication. And before that, we shall see later that that unitary group may not be cyclic for integers other than this form as well. So here we just, whatever we showed is restricted to these kinds of numbers. Okay. Now, if we look at this, then notice this. If you look at the solutions of z square equals 1, then what do you have? Very simple. We have been doing that forever. Negative 1, 1. And this one is a cyclic group, right? And who generates it? Negative 1 does, right? So this is a cyclic group generated by negative 1. Now, on the other hand, if we are looking at the solutions of, say, z cube equals 1, all right, so we know that there is one solution already, and the other two solutions are complex numbers. Now, if you didn't take a course in complex numbers yet, don't worry about it. We are just going to calculate it out. So say one of the solutions, or solution is, of course, z equals 1. But how do we get the other solutions? So we may do this. So see this here. Say we have z cube. Now I'm going to write this as cosine of 2 pi plus I sine of 2 pi. All right. So now remember the Euler's formula. This is going to just become e to the power 2 pi I, right? That's what this will be. So what happens is the equation z cube equals 1. What does it change for us to? It changes to this for us, right? So who z will be then? Z will be then the cube root of this number, right? Okay, here we go. Okay, so let me just erase it here and put a 3 here. Now they are becoming too tiny, so let me increase our font size. Very good. Okay, so that's what this becomes, right? And this is how much then? So, and again, this gives you one solution, right? So this is cosine of 2 pi over 3, again by Euler's formula, and then I sine 2 pi over 3, right? So that's a what? That's a complex root, right? So one value of z is 1, okay? And another value of z is what? That comes out to be this much, right? And then if you, and this will be, what will this be? This would be negative, so this is 2 pi over 3, so this will be 1/2 plus, remember sine 2 pi over 3 would be what? Square root of 3 over 2. Remember your standard triangles in trigonometry, right? So, and so this is again a cube root of 1, right? Okay, so that's what we got. This is a cube root of 1. And you can see this here. So this is a cube root of 1, and if we do this, if we take the square of this number, we can multiply just by using the fact that I square is negative 1. Okay, so if we expand it, okay, all right, what do we get? This is a number different than this one. Okay, actually it's just the conjugate of this in this case, right? So this is another cube root of 1, right? So we got what? We got 3 cube roots of 1 here. And then what happens is this. I mean, one of them is this, right? Right here. Okay, and then you have this squared, okay? And if you go ahead and just take the cube of this, all right, cubed, then this would be, this is going to become 1. So what happens? Cube roots of 1, they can all, there are 3 of them, because if you start repeating it, of course it will be 1 times this itself, so the numbers will start repeating themselves. And you remember this, that they all live on the unit circle, so you can see their cyclic nature very well. I'm not going to stretch this presentation too much beyond. Okay, so these are cube roots of 1, and with respect to multiplication, okay, multiplication, they will form a cyclic group, right? Because you just saw that they're all generated by just this element, right? So you can see this whenever we have like an even root of 1, we will have 1 and negative 1, 2 real roots. The other will be complex, will be non-real numbers, okay? So here, these are the cube roots of 1, and they form a cyclic group, okay? Cyclic group with respect to multiplication, right? Okay. And I just wrote the generator here. I mean, in general, if n is a positive integer, okay, n is a positive integer, all right, then what you can see is, if you are looking at 1 to the power, or if you are looking at the nth root, okay, like this, you can always just instead of so you can let me just copy it, that will be faster. I was just debating. Okay, so I can replace 1 by this. All right. Okay, and here we got what, simply 1 over n. Okay, so this is going to be cosine of 2 pi over n plus I sine 2 pi over n, right? And so of course this will the powers of this will generate different nth roots of 1, but our interest is this, that they will all form a group with respect to complex multiplication. Okay, and that group will be generated by, one of the generators is this right here. Okay, so the, you may call it the group of, okay, nth root of unity, and I'm not going to be mentioning the multiplication again and again, because from now on we we shall just try to recognize it when it's plus, when it's, when it's a product. So just do the assignment that I asked you to do, and I'll see you in the next presentation. All right.